Let's talk about avgas versus autogas. Avgas versus autogas. Autogas. All right. So as I mentioned already, there's a lot of STCs. STC. Well, let's do a complete thought here. So there are many aircraft. There are many aircraft.
Like that, but this one is mine.
Aircraft that use an STC to operate on, and believe it or not, they call it, I'll say autogas, sometimes called MOGAS.
Have a problem? Add MOGAS.
This is only possible for aircraft that have a minimum, or that have possible aircraft 8087. Otherwise, it's not going to work, because the highest octane rating we're going to get at the store is 91, right?
Right.
Hey, Kevin, what is that? Mo goes after autogas?
Right there, it says MOGAS.
Oh, MOGAS.
MOGAS, M-O-G-A-S, like motor gas.
Oh, okay.
I don't know, that's what they call it. So, all right, so it's not all bad. Some people like it. So what's my benefit?
Cheaper.
The benefit of MOGAS. Well, I didn't write that one, but I guess I will now. Okay, cheaper.
Mo flight time.
Cheaper. I don't really know about this, so I'm going to write it, but that's why I say possible valve issues with lead. Although I couldn't find anything conclusive that would explain what the issue is and what the problem is. So definitely have lead fouling. Lead fouling is a big deal. So possible benefits of MOGAS. I should put no lead fouling, no possible valve issue with lead, so no lead fouling of plugs. And this sounds like something I made up on my own, because I'm sure it is. Very clean intake ports.
Yeah, I remember you were saying that because Chevron has the Techron in it.
Yeah, Chevron and Shell, they both have. All right, what are the cons?
Not as regulated.
Okay, well, cons of MOGAS. Let me see. There you go, number one answer. So, see, MOGAS is not as regulated. So quality control, so QC, quality control issues, contains, well, MOGAS contains alcohol and other chemicals. Alcohol and other chemicals not compatible with rubber, not compatible with aircraft rubbers, because there's different kinds of rubbers. This is kind of a same thing. So lower QC, quality control, higher volatility. What does that mean? So MOGAS has higher volatility. Why do I care about that? Sounds like it's going to burn better, right?
Mm-hmm.
Vapor lock.
Anybody remember what the volatility problem is?
Vapor lock.
Mark said vapor lock. I don't know.
Vapor lock is correct. Sorry, I was looking over at Julian said that he's having problems trying to log back into Zoom. I don't know what I can do about that. Higher volatility. Oh yeah, so we may have vapor lock problems. So much higher vapor pressure. Which again, leads to vapor lock. And also does not contain preservatives. Due to high turnover. In other words, the gas station is going to go through a whole lot of gas really quick. It gets used up really fast, and so they don't really have to deal with this preservation. But an aircraft is a much slower turnover. You know, we're going to fill up our tanks in our aircraft. Maybe it's going to set for a month or two, and so that's a consideration. It is not with car gas.
How much longer would nav gas last to car gas? Do you know?
I think it's a really long time. I mean, really long.
I heard that my boss was saying out at the airport that he had a barrel that was unopened, didn't touch air from like the 80s, and he said he used it in his own private aircraft, and he said it ran fine.
Was it your boss or was that Larry Johnson?
My boss said he did that.
Okay. I thought Larry Johnson said the same thing. So
yeah.
All right, chemistry. Chemistry. But not too much chemistry, just a little bit of chemistry. All right, so fuel. Fuel is a high. Everybody doing okay? Keeping up?
Yeah.
Yep.
Okay, J-Rod says yes. All right, chemistry. Fuel is a hydrocarbon. Hydrocarbon. And if we dissect that, that must mean hydro, which is water, and carbon, which is, so water and carbon?
Mm-hmm.
No.
Oh.
Listen to me.
Hydrogen.
Hydrogen and carbon. Hydrogen and carbon. All right. Okay, I'm not going to do too much of this. Don't freak out here. No, I'm not even going to say that. Yeah, what the heck? I wrote it. So each molecule is 8 carbon atoms and 18 hydrogen. And for those of you that had electricity, we could probably decide by looking at it if it's a insulator or conductor, right?
Yeah.
All right. So fuel. In order for it to burn, it needs to be in a gaseous state. What do I mean by gaseous? Because it is gas. So therefore gaseous?
No. It needs to be air.
There, I like that. It's got to be like air gas, not gas. No. So it has to be not liquid anymore. So not only, number one, does it need to be gaseous to burn, but also it needs oxygen burn. It needs oxygen to burn. All right, now we have to think about, and I talked about this a little bit ago, weight versus volume. There's a difference between weight and volume. Oh, Julian says he gets a message saying, because Julian probably changed his name to MJ. So Hang on, I gotta help
MJ is laughing.
because I deleted anybody.
Oh my god.
Let me see. What can I do? Uh-oh. Because it's in progress, I can't do anything for him.
Permanently removed.
So let him know that's because he changed his name to MJ.
Wait, who?
Settings. I wonder if there's a setting.
Tell him he's been dropped. It's nice.
Oh gosh, he's gonna poop. You know that you can change the color of your thumbs up and thumbs down.
What'd you say, Zach?
What?
Yeah, to your skin
Watching the
tone.
Fairly Odd Parents.
Yeah, my girlfriend is. Yeah. Good old cartoons behind me.
I don't want to be Simpsons yellow.
MJ.
Yes.
MJ says.
Why?
There's always multiple of you, man.
Okay.
I don't even know
I'll
who to
try
talk
now.
to.
Devin, you let him know that he could try again. I changed the setting. Yeah, well, August did the same thing. So
Apparently, you can share files in the chat room.
yeah. All right. So here's the deal. If you change your name to MJ, I'm going to go through and delete you. So don't change your name to MJ unless you're MJ.
And you just change it.
And if it gets too bad, I'm just going to delete MJ. So, okay. So fuel. All right. Who just came in? Nobody's going to admit to it.
Sound like the Matrix.
I know.
I
Okay.
mean,
All right. So we need oxygen to burn the fuel. So let's talk about, all right, air is by weight.
Why wait?
All right, so we talk about air by its actual weight. We have 75.3% nitrogen, which is an inert gas and it doesn't burn. We have 23.15% oxygen. Oxygen and 1.5, who knows what the 1.55 is?
Miscellaneous stuff, right?
Other cow farts and stuff like that. All right. Hey, Devin, did those two guys make it back in? Air is by volume. No, not answering. Okay. By volume, 78%. 21% oxygen, and 1% other. All right. So
What I have kind of a question.
you have kind of a question?
Yeah, well, because you said air is by weight and then air is by volume. It goes 75.3, but then 20. What makes it so different? Like the 2% on the oxygen.
What weighs more versus what takes up more space?
Thank you.
No. Okay, and then we're going to talk about mixtures. Okay, so I told you earlier, and this was the word I used, there's this thing, and we're going to say it a lot, called stoichiometric. S-T-O-I-C-H-I-O-M-E-T-R-I-C. Stoichio. Yep, Iometric. Stoichiometric. PK, you've been muted. All right, stoichiometric. What stoichiometric is, it is considered a chemically correct blend. And I want to stress this word chemically, C-H-E-M-I-C-A-L. Chemically correct blend. I'll put a fuel, and oxygen. O-X-Y-G-E-N. All right, chemically. So that's if you are a scientific person and you take a look at the chemical makeup of the fuel and the chemical makeup of the oxygen, and you count it out and you blend it, you say, I need this much oxygen to burn exactly this much fuel. All right, but it doesn't really work that way in the real world in the engine, because if you think about how fast the valves are going up, opening and closing, how fast the piston is going up and down, how little time everything has to mix, perhaps this oxygen molecule that's way over here and this fuel molecule way over here, they can't match. So, and so you may need more oxygen by weight or volume than fuel to actually have enough oxygen to find all of the fuel. So Devin, I don't know what to tell them. I guess it's because they changed their name to MJ, and I kicked all the MJs out except for the one who I could see. So I guess what they'll have to do is I'll post it and they can just catch up.
Okay. Yeah, I'll let them know.
Did you send a link of where you're going to post it?
I'll try and do it on YouTube, where I always do it.
Okay.
Oh, kind of a question as well. When you join this chat,
It doesn't have actual questions, just kind of questions.
Do you just always click on the same email that you sent from, or are you going to resend an email every day?
Should be the exact same link, always, all the time.
Okay.
There's a number that's attached to the link, and you can just copy that number and post it to join.
Here,
Yeah, it's on Canvas as well.
Are you able to
That's the number
email your link, your YouTube link as well, Kevin?
Probably. Yeah. Or somebody can do that who's not paying attention to what I'm saying. Just go on YouTube anyway. Okay, so chemically correct blend of fuel and oxygen, which is to say that all the fuel is burned. All the fuel is burned. So again, another way to say it, in a stoichiometric, mixture, there is neither an excess of air or fuel. And a stoichiometric, chemically correct mixture is defined as 15 to 1, which is, I'll put this here. Also, it is a 0.067. Now myself, I like to think in the ratio department. I don't like to use the decimals, because to me, I can see the 15 to 1. I can say, okay, you have 15 parts of air and you have 1 part of fuel, but the 0.067, I kind of have to convert it. So I tend to talk more as the ratio. But what this 15 to 1 is saying is that is 15 pounds, not weight or volume. I should tell you. Notice that's weight, not volume, of air to 1 pound of gas. Or 0.067 pounds of gas to 1 pound of air.
No, the more you adjust it, it'll, like, let's say you go full rich, it'll be like 15 to 15 or 15 to 10 or whatever.
Sorry. So would
Right.
somebody change their name to Kevin Gehring to everyone? I don't know. Well, if there's an extra Kevin, guess what? You're getting thrown out. Uh-oh.
Keep your name.
Yeah.
Yes.
Hey, you should change it pretty quick there. Hey, don't forget, I know this is all fun. That score, I actually have to look at that at the end of this. And if your name isn't your name, then you don't get credit for being here. Okay, so let's see. What about the nitrogen, since it does not burn? Right, it doesn't play into this. But what the nitrogen does do inside of the cylinder is it heats up and it expands. So also what nitrogen bonds with leftover oxygen to form nitrogen-based emissions. Well, that would be true, but if we're talking about purely stoichiometric, then there is no leftover oxygen, right?
So what I was asking though, when you say is a stoichiometric mixture, so that means when, like, if you were to bring your mixture in or whatever, does that mean it's still going to be it's not going to be 15 to 1 then, right?
Yeah.
So
that's what the mixture is, 15 to 1. Very close to it.
Always though.
Pretty close.
Okay.
Not always. There's going to be a range.
Because when I think mixture rich, I think more fuel in there than, or like more than 15 to 1.
Yes, that is what rich means, but we're going to get to that.
Oh.
But that's a good point. Let's see. So I just have some other notes here because I think it's cool. So 1 pound of air is about 13 cubic feet. All right. Or we could say 6.7 pounds of gas to 100 pounds of air. Why not? Or what did I say here? Or 6.7 pounds of gas to 100 pounds of air. That's a little over 1 gallon of gas. Yeah, a little over, well, fuel is six pounds, so it's a little over one gallon of gas to 100 pounds of air. 100 pounds of air, how much is that?
100 cubic feet.
That would be a room that's 10 by 10 by 12.39 feet. So, and that's how much it would take to burn 1 gallon of gas, which is a little smaller than the room I'm sitting in. But you can't see that, so that doesn't mean anything to you. So, all right.
That's just so confusing. Because you can burn a gas generator in a room that's feeding in air with, like, it's just so confusing to me.
Well, maybe we'll get you unconfused. So what I want you to know right now is, what is stoichiometric? It's the chemically pure, correct mixture that will burn all of the gas and all of the air and have neither one left over.
But that's not the most efficient for power, is it?
No, not necessarily. No. Not at all. Nope. Because like we talked about, you got to have time for it to mix, and it may not be. So that's not necessarily your best power at all. But it's the chemically pure, and that's where we can start with, knowing that it's 15 to 1. All right, so we're going to talk about that, and we have stoichiometric. Let's talk about a rich mixture. What time are we supposed to be done? Oh, it's 50. Okay, rich mixture. There's different numbers on this, but I want to go with what's easier to remember. And I'm going to use 8. So as little as little as 8 parts air to 1 part gas. Remember, you always need more air than gas, and that's a good thing. It's 750. We got a Shrek in the class. I think I need to drop Shrek.
Y'all really think this is a joke, huh?
Show your face.
Apparently.
I can't.
Like, what is this?
But
What? Why do this?
all right, little as 8.
I think I know who it is too.
Well, we'll just let it slide. It shows up on the, I think on my statistics when I pull it. It's a big old spreadsheet that shows all kinds of stuff. So you'd be surprised. All right, so as little as 8 parts to 1 part gas by weight. Remember, it's always by weight, by weight, by weight. So I'm going to say it again, it's by weight. That's always going to be a problem for us when we talk into how stuff by weight can still burn, can still burn. So what happens when we get down to 7 parts of air to 1 part gas?
It won't
It
burn.
won't burn.
Very well.
It won't burn. That is correct. Okay, so I guess can still burn. And so that ratio is 8 to 1 or 0.125, which is 1/8. By 8 is where we go.
1/8.
1 divided by 8 from right there. So, okay, 1 divided. So a rich mixture, let me see, we'll put that here. We'll put this here, 1, 2, 3. A rich mixture. A rich mixture burns slower. Burns slower than a correct mixture. And I'm going to use the word correct because I don't want to use the word stoichiometric because that's misleading then. So a rich mixture burns slower than, I'm sorry, did I fit rich? Yeah, rich mixture burns slower than a correct mix. So there's speed involved with this. And that's going to come into play in a little bit. We're going to talk about why things do certain things. And it's because when you get on the rich side, I got to be careful I say it. I'm going to bring it all together, but don't just think that, okay, that's the slow and then it goes the other way. It's once you get on either side of stoichiometric, you start changing the flame front, how fast it goes. A rich mixture will burn slower than correct, but it's faster than a lean. So we'll talk about lean mixture now. Lean mixture. All right. So as much as 18 parts air to 1 part gas by weight. And that is shown as 18 to 1 or 0.055. All right, lean mixtures. Burn very slow. So if I were to, well, I'll get into a little bit, but if I were to look at a chart, I would say, okay, stoichiometric burns at 1 speed. It's going to start slowing down as we get towards the rich, and then it'll stop. All right. And you can look at that speed, and then you can go the other way and you can say, okay, well, as I leave stoichiometric and I go towards lean, it's going to burn slow, slower, slower, even slower than rich. And it's going to keep going slow, slow. So it's the one that will burn the absolute slowest, which in theory brings us to one of the questions from last semester, or last class, whatever that was, about why some engines actually have a backfire and what caused a backfire. And I think the answer was actually a lean mixture. And the theory is that the mixture was so lean and then it burnt so slow that by the time the intake valve was opening, it was still actually burning. The fuel was burning. It would light off the fuel coming into in the intake manifold.
Mm.
Right, so lean mixture burned very slow. Oh, that was it.
That's pretty long.
Oh, go ahead.
Oh, I was gonna say that's a really long time because I mean from the
It's I don't think it's true. I think that's a little weird. All right.
Could that also cause an afterfire?
No, remember afterfire is when it goes out to the top line. So that is gas, unburned gas being lit off.
Got it.
All right. So here's a chart that shows that. And so effects of fuel air ratio on flame propagation. And what this chart is actually showing is, laser pointer, I already drew on it. So this is not stoichiometric, but best power, which we'll talk about. And if I say rich is 8-to-1 and lean is 18-to-1. So remember the number, it's kind of backwards a little bit. So rich means more gas. Lean means less gas, but you're seeing this higher number. So it's easy to get them backwards. So you have to remember that this is the air part. So there's more air than fuel. And we look at 8-to-1, I try to remember, we're getting closer to 1-to-1, which would be 1 part oxygen to 1 part air. Would that be rich or lean? You think, well, that'd be really rich.
Really rich.
That's kind of the way I run it in my head. You go, okay, wait, it's closer to 1-to-1, which is not going to work. So that's rich, rich, rich. So lean is a whole bunch of air. So if we look at it, this chart is kind of representing, well, it's the flame propagation rate, but figure this is the time of the burn. So when it gets to this point right here, it's just going to stop. There's no more burn. So this is as slow as it can get. And we look over here and go, it can get a lot slower. Keep going slow, 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 slow. So that's what I mean by that.
On the rich side, does it keep on going down as according to this graph?
No.
If it gets like more rich? Okay.
No, figure right here where this X is, that's the end of any sort of burning. After this, it will not burn.
So just plateau right there?
Yep, plateau right there, it just stops.
Okay.
And then figure
So
right
on
here, it
your-
stops burning.
You
On
said
your
earlier.
airplane, can you only at full rich? Is it only 8-to-1, or is that where it cuts off?
Yes, that's where it'll stop to run. It'll stop running.
You said 7-to-1 it'll stop, but then on the lean side, is it anything above 18-to-1 it'll stop?
Yep.
So if it's
So
19-to-1?
let's just say we hit 19-to-1. It won't run.
Okay.
Not going to run. Now, I'm being a little general on this, but it might, depending on the engine, it might actually run in the 19-to-1 range. Probably not real well, and it probably run at 7-to-1. Probably not real well. But
Okay.
yeah. What's my next thing?
Would it smoke a lot if you were running at 7-to-1 or 8-to-1?
It would smoke more on the rich side, not on the lean side.
So that's what happens when you pull your mixture out, just going below 18-to-1.
Yes.
Okay.
All right. So lean mixture burns very slow. That's what I got there. I'll put this one here. So note on burn speeds. Note on burn speeds. Both rich and lean burn slower. Slower than best power. Lowest power. But a lean mix has the ability to burn much slower. There.
What is the mix for best power about?
Well, we're going to talk about that.
13-1.
and how we figure out how to get there and all that good stuff.
On Engine Masters, it's always like 12.8.
It's going to depend on the engine and the mixing and everything. All right, I've got a bunch of stuff here. We don't need to go over that because I already said a little bit leaner and a little bit richer burn at the same speed. Pull this back up. A little bit richer and a little bit leaner burn at the same speed. A little bit richer, a little bit leaner, same speed. Max lean can burn much slower than max rich, which I already wrote that. Max lean burns a lot slower than max rich. Burn speed is important due to where the peak pressure point of the combustion happens. That's what I've got going down here is that peak pressure point. And this goes back to our last class. We talked about the rotation of the crankshaft coming up. And if I had a peak pressure wave right here at top dead center, it's just going to force all this pressure straight through the crankshaft, straight into the bearings. We're going to lose power. So we want this peak pressure to actually happen more over here when the crankshaft is starting. I think this picture is more accurate. When the crankshaft is starting to come back down the other way. And of course, by the time we get down here, we want it to be expended. So we have to care about where that peak pressure wave is. Not only that, but it has to do with detonation and all kinds of stuff. So I will put that. Let's see.
Can you hear when engines are running lean? I've always heard that people they say they can feel it, or they might be able to hear it if it's like rich or lean.
You can really feel it in an aircraft engine. And there's controversy on why you can feel it. And it's funny. So the old school way of thinking is that what you're actually feeling, and it's actually a leaning technique. They'll tell you to pull the mixture out and lean until it gets rough, and they're riching it in until it gets smooth. And they say, well, why does it get rich? I'm sorry, why does it get rough? And then people say, oh, it's getting rough because you're having a lean misfire. And it's not until recently that people are actually saying that's not true. And there's all these non-truisms going out there. And case in point is when you get to a certain point, it doesn't lean misfire, it just stops running. And when you can experience that when you actually pull the mixture in an aircraft all the way out really fast, it doesn't lean misfire a few times before it stops. It just stops like that. Mm-hmm. And so what they're saying now, and this is the new school of thought, is that rather than it being some sort of lean misfire, you're actually seeing, especially in carbureted engines, where the carburetor, the fuel comes from one central location and has to find its way to all 4 or 6 cylinders. It doesn't do it uniformly because the fuel is just kind of stupid. It just, some little more is going to go one way than the other. And that's just the nature of the beast. And so what you're actually experiencing is because when you start getting that lean, you're going to have a wider gap in the power between cylinders, and you're feeling that. You're feeling one cylinder has much more power than the other one. So you are enriching it back until the power peaks of each one, of the power on each cylinder, more closely matches, which is more what I believe.
So it's kind of like a misfire, but it's just starved of fuel, basically.
No, they're all firing equally. They're all firing as they're supposed to. It's just one has way more power because it has more of an appropriate, closer to best power mixture than another one. And I'm going to show you power curves and stuff here as soon as we get through this, so which is almost done. So let me just finish this up real quick. So burn speed is important. Burn speed is important. Is important due to where the peak pressure point happens, which is the PPP, peak pressure point of combustion happens. And like I said, you want it to happen as the crankshaft is rotating around. Should the peak pressure happen, the peak pressure point happens after top dead center? Happens, it better. After top dead center. And the last point I think I want to make before we take off is we always have to be careful of a byproduct. This is actually number IV, a byproduct of combustion is carbon monoxide. Or CO. CO is a colorless, odorless gas. That is deadly. That is deadly in concentrations of 4 parts in 10,000. So it doesn't take much to kill somebody. And the other thing weird about carbon monoxide is it bonds to your blood, the oxygen carrying, the red blood cells, and it doesn't want to leave. And the remedy for that is time and or hyperbaric chamber under pressure. So no fun. All right, so that's a good place to stop. Actually, my notes say right here, that's the end of one. So I don't know how they managed to do all of that in 4 hours when I thought I'd done it in 2. I don't know. Because that was 4 hours, right?
Yep.
Yeah. Okay, so we will meet again tomorrow. And hopefully tomorrow we won't have a whole bunch of MJs.
Yeah.
Oh, Shrek.
And Hector should change his name from MacBook to Hector.
I already did.
Yeah. Yeah, it says MacBook.
Yes.
Still says MacBook, yeah.
Well, he's got his picture, so I know he is. But it would be very helpful for me to give you the appropriate credit for being in the class if your name is recognizable by me. So, all right?
All right.
It can't be my name because I could show you your attentive scores the other day from when I ran the sample class. Oh, it's got them. So,
hey, Kevin, really quick, is that 4 to 10,000 parts per million?
It's deadly, and four parts of carbon monoxide so 4 parts in 10,000. I shouldn't probably have wrote it as
okay.
4 parts.
Kevin, what I was confused about earlier on the stoichiometric, you were saying earlier that it won't run, or it will run, but it's not stoichiometric or whatever, and a 10 by 10 by, let me go back to it. Does that mean if you have an engine on a stand in a room that's small, you can't get enough air? That's what I was kind of confused about. Does that kind of make sense?
Yeah.
Just 100 pounds of
If you put an internal combustion engine inside of a room and sealed up the room, started the engine up in it, it would only run for a little bit and it would die. It would run out of oxygen and not run.
Oh, okay.
Yippers. All right, let's see. Yeah, no goofing off. Are we going home today early? Actually, you should have been home for the last 4 hours. So yes, you are going home early. Kevin did unblock.
I think I got a text from.
All right, I'll see you guys tomorrow at 3:30.
Yep. Thanks for all the knowledge.
Thank you.
Thanks.
Have a good night.
See you tomorrow.
I'll later.
Thanks for the knowledge. Just making sure you.
Yeah.